Okay, hi everyone. My name is Dr. Salah Zaidi. I'm assistant professor in University of Baghdad College of Engineering. This lecture is a part of my course in structural dynamics submitted to master students in our department. The aim of lecture is to show how SAP software can be how SAP software to be adopted and determine the natural frequency of indicated slab on a grade. The slab on a grade is assumed to be supported partly on soil and partly on the edge beam. Previously in our lecture, this slab has been transformed to indicated analytical model where unicular subgrade reaction is used to simulate soil and perfect hinges are adopted to simulate the edge tie beam. Our aim today in this lecture is to resimulate the slab using finite element simulation with SAP software, and to compare between two results, the results of analytical analysis and the results of finite element simulation. Our analytical analysis based on the concepts of shape, relay method, and we have this final relationship to determine the natural frequency of the system, fundamental natural frequency of the system. When we when we adopt a numerical value for the system, such as in this homework 8.5.1, we assume that we have a slab on a grade with width of 6 meter and a thickness of 150 meter, compressive strength of concrete of 25 megapascal, and the coefficient of subgrade reaction for the underneath soil is about 10,000 kilopascal per meter. When we use these data and the aforementioned analytical relationship, we will have a natural frequency about 171 radian per second and a time period of 0.0367 seconds. Okay, this homework to be resolved using finite element with SAP. Start our process to run the SAP 14 will be adopted here. SAP 14 will be adopted here. Okay. The first step is to change the units to metric system. In dynamic problems, it is preferable in general to use basic units to avoid any problem regarding to the how to define the ground acceleration if necessary in our problems. Then go to file, select, try to open a new file, start from a grid. Okay, we will have two grid lines along X. Let us return to figure to make the description more clear. I try to simulate in SAP model to simulate a single panel of the slab on a grade. Therefore, I have two grids along x-axis. Okay, and I have two other grids along y-axis. Then and I have single story. Therefore, I have one grid along z direction. With this option, I will have a single panel. The dimension of panel, the width of panel 6 meter as indicated in the given data of our example. In analytical model, we need no information about the length of a slab, as the slab in our simulation been has been modeled as perfectly one-way slab that deflected into a cylindrical shape. Hence, we have no information regarding to the length of the slab. But in finite element model, it is necessary to assume the length of the slab. The length of a slab here is assumed 18 meter. That is mean the length, the ratio, the aspect ratio of length to width of the slab is about 3. This relatively large aspect ratio is adopted to make the slab behave as a one-way slab, to have a similarity between finite element simulation and analytical simulation. Okay, let us save the model. Okay, I will overwrite about this file slab on grade 18.04.04, the date of file generation. Okay, the first step, uh, actually SAP model is built can be built based on indicated pages, build down menus. The build down menus have been prepared in a logical sequence that when one follow the pages in a logical sequence, the model will be complete. Start with define. The first step is to define material. I will modify the material properties, concrete material properties that has been prepared in imperial unit. Uh, I will modify material properties to be suitable to metric system that usually adopted in metric specifications instead of the soft metric system that adopted by SAP. Hence, instead of 23.5, I will adopt 24 for density of concrete. The Young modulus of concrete can be determined from ACI code. I have for 4,700 times the compressive strength to the power of 1 half to have 24,870. 24,870. 24,870 megapascal. Okay. Other Poisson ratio, okay, accepted. Coefficient of thermal expansion is not related to our problem. Shear modulus G is determined automatically or modified automatically by SAP software according to the relationship of mechanics of material or theory of elasticity, where G equal to E over 2 over 1 plus Poisson ratio. Okay. Finally, to make the description of a problem complete one, compressive strength is changed to 28 megapascal. The compressive strength is not necessarily here as we have no design aspect in this problem. Okay. Okay, I try just to change the name of material of sub C prime equal to 28 megapascal. Okay. The second step is to define area section, to define the slab thickness. Okay, slab thickness. Okay, here in slab thickness, we have different options. We have shell or plate. In shell model, the membrane and the flexure stiffnesses of slab, both of them are included. While in a plate, we neglect the membrane stiffness of the slab and focusing on flexure stiffness of it. Shell is the most general one and will be adopted here. We have another sub-classification, sub-description regarding to thin and thick plate. In thin plate, the or thin shell, the shear deformation is neglected. Okay, what and the Kirchhoff plate theory or shell theory is adopted. That is mean the model will be based on the kinematic assumption of a plane before loading, remain plane and normal to the neutral axis after loading. When thick plate is adopted, shear deformation is included. For our slab that has aspect ratio of that has width of 6 meter, depth, length of 18 meter, and thickness of 0.15 meter, these aspects represent a thin slab where thin shell can be adopted and shear deformation can be neglected. Okay. What other we should modify the slab thickness 100 millimeter. In SAP, different slab thickness, different plate thickness can be simulated to membrane part and bending part. Here we have a common thickness of 150 millimeter. The second step is to draw the slab. As I have here a single panel, therefore a quick draw can used to draw the panel. Quick draw. Okay. I go to a view. I'm sorry, I have some problem. Okay. I select full object to see full shape. Okay. Here also I will select full object. Okay. I try save continuously to avoid the possibility of loss of my data. Okay. The second step is to define the load pattern and load case. That is mean to define the loads. As discussed in our lecture, one of the most powerful capability of SAP is, is the concept of load pattern and load case. In load pattern, we describe the spatial distribution of load and say nothing about the temporal distribution or how we will treat this load later in our analysis process. While in load cases, we merge the spatial distribution of spatial distribution of our load case, our load pattern that have been defined previously with suitable temporal and select temporal function and select suitable analysis, for example, static, dynamics, elastic, buckling, and so on. Okay. Let us start with load pattern. From load pattern, I will change the load pattern name from date to self weight to be more inductive. More inductive. Load pattern actually represent a dummy name that has meaning for me and for anyone who will use my input file or read my report, and has no meaning for the Slab, for the software. What is important in software is the load type. Load type. This load pattern will be considered later as dead load, depends on type and not related to self weight. If I change self weight to live load, load pattern name from self weight to live load, software still deals with this load pattern as dead load. Self weight multiplier indicate if the on weight of structure to be included or excluded. One to include the on weight. Okay. Uh, the second is the next step is to define the mass. SAP offers three different ways to define the mass. Additional lumped masses may be added. We may transform predefined load into mass or use both of the two techniques. Okay, here we will define mass based on self-weight load pattern that defined previously. Okay, the third step is to select the cases. By default, we have two cases that generated by SAP software. The first one related to linear static analysis, and the second one related to model. I will modify the dead the dead load case. Load case name will change to self weight to be more compatible with the related load pattern. Okay, this load case is a static linear one. It's out of my scope as I try to determine the natural frequency, but it's still useful and make my work more compatible and more complete. Then I go to to model analysis. Here in model analysis, I will I will solve the resulting characteristic equation to determine the natural frequencies and mode shapes. This procedure similar to determine the root of characteristic equation, but here we have a mass matrix instead of mass in single degree of freedom. Here we have multi-degree of freedom, hence we have mass matrix instead of mass in single degree of freedom, and we have a stiffness matrix instead of a stiffness in single degree of freedom system. Therefore, the resulting characteristic equations that should be solved to determine the natural frequencies is highly complicated to be solved by hand calculation. many of enhanced algorithms have been developed to solve this polynomial equation. Two of them are available in SAP environment, eigenvectors and Ritz vector. We will use actually the difference between two algorithms will be discussed later when we talking about multi-degree of freedom system in our course. Okay, eigenvector will be adopted here. Uh, uh, the two uh, lowest frequencies, the first 12 lowest frequencies to be determined by SAP. Actually, the first six lowest frequencies are in general sufficient in our case. Also, the meaning of different mode shapes and how to select the suitable number of mode shapes that adopted that to be adopted in our analysis will be discussed later, okay, in multi-degree of freedom system. Okay. Finally, I have two aspects that should be assigned before run the model. The first one is the finite element mesh of slab. I select the slab panel, go to edit area, divided area. I will divide area to a mesh of 0.5 meter in each direction. 0.5 meter in each direction. Okay. Turn off the shrink mode. Then I select the select edge nodes. I select edge nodes. Edge nodes along long sides and go to assign hinge precedent. Okay. With this step, I simulate the hinges at end of the slab, hinges that adapted to model the stiffness of edge beam. Finally, I should assign the Winnicler foundation. I should assign the Winnicler foundation. Go to select by properties, select area section, select my slab, then go to assign area spring and input the value of my the stiffness of my subgrade reaction. According to my example, the subgrade reaction has a stiffness of 10,000 kilopascal per meter. Okay. Finally, to focus on the vertical vibration of a slab and to exclude all mode shapes and all frequencies related to lateral vibration of slab, I will select XY plane. Okay. My model is ready for run. I run the model. Change the deflected shape from self-weight that related to static analysis to mode shape. shape. Okay, to see the first mode shape. Okay, as indicated in the deflected shape, the mode shape is a cylindrical one. That is mean it is similar to that adopted in analytical model. And I have, according to finite element analysis, I have a time, a fundamental period of 0.3707 second. According to analytical solution, actually I have a time period of 0.0367. That is mean the two solutions are so close to each other, and the approximate analytical solution that based on relay shape and the concept of generalized single degree of freedom seems so accurate for practical analysis. Thank you very much for listening and your